Hello everyone. So in this video we'll talk about the oxidation reduction potential and the hydrogen half cell. We are proceeding with our material in electrochemistry. If you still remember that last time in the last video we talked about the galvanic cell. We were able to name the main elements of the galvanic cell, the main compartments, the cathode half compartment, the anode half compartment, and we were able to assign the role of the salt bridge in preserving the electron neutrality of the solution. And we talked about the cell notation, so each cell is being represented by a notation, and we talked about it last time. In this video we'll complete our material in electrochemistry, and we will talk about the hydrogen half cell. We previously talked about hydrogen couple as well. If you still remember, the hydrogen couple is H plus H2. This is the redox couple of hydrogen. We'll talk about what's called reduction potential in this video. Now, before starting with the material, I need to mention what's called electromotive force. I need to define something which is called electromotive force. Now, the electromotive force, if we still remember that in the case of Daniell cell is a specific galvanic cell. It contains of Zn2 plus, Cu2 plus, Cu. The galvanic cell can contain many elements other than Zn and Cu2 plus. Daniell cell is a specific case of the galvanic cell. The huge umbrella is the galvanic cell, and we have a specific case as Daniell cell. It's named after the British scientist Daniels. Okay, that's why we call it Daniell cell. Now, in the Daniell cell, if you still remember that the voltmeter indicates the voltage UPN is equals to 1.1 volt. If you still remember that. Now, and we talked about that, if you still remember, in the galvanic cell, that the current was too low, so that we used milliammeter to calculate the current, if you still remember, and the voltage, the potential difference is UPN. You know that the voltage is equal to the potential difference. And you know UPN, we mainly assign UPN for the potential difference of the batteries, because UPN, the P stands for positive, negative. The N stands for the negative. Positive, negative. So the UPN of the battery is the potential difference between the half cells. So it's V for Cu minus V for the Zn. Or in other words, we can say it's V for the cathode minus V for the anode. This is more general. Okay. Now, let's talk. What does this mean? This means that it's E minus IR. Now, E is the electromotive force. IR, the I stands for the current and the R stands for the resistance. Now, IR is almost null because the the current is almost null inside our cell. The current is almost null inside our cell, so it's almost I tends to 0. So IR is almost 0. Okay, so we come to the conclusion that UPN is equals to the electromotive force. So UPN is equals to E in the case of Daniels is equals to 1.1 volt. So E, the electromotive force here, is 1.1 volt. Now, what's the definition of the electromotive force? The electromotive force of a cell equals to the potential difference between the electrodes of the cell, the potential difference between the electrodes of the cell, the cathode minus the anode when it's not operating, when it's not discharging. Okay. Now, I'm interested talking about the cathode VCU minus VZN. The potential here, the potential difference. Now we know that the UPN is the potential difference now the potential difference of the cell is equals to the electromotive force, but we can't really know we can't clarify here what does potential difference really means. And this is what does really means: V for the cathode minus V for the anode. And for this reason, we will in this lecture, or in this video, we will understand the oxidation reduction potential of elements. We will construct the hydrogen half cell, and we will understand the role of hydrogen half cell. Okay, we will understand the role of hydrogen half cell. So we will start with the first cell diagram. We have the cell notation. Through the cell notation, we can assign the elements of the galvanic cell. So here we have the salt bridge. Here we have this is the anode. As you still remember, we start with the anode and we end up with the cathode. So here the Zn strip, here the Zn2 plus. We have a spectator ion as well, but I'm not really interested talking about the spectator ion. Here we have Ag, here we have Ag plus in the solution, and the electron flow from Zn from the Zn electrode to Ag electrode. From the anode, the electron flows from the anode to the cathode, while the current flows from Ag to Zn. It's the inverse of the electron flow. Now what I'm interested in, what did the voltmeter indicates? What did the voltmeter indicates in this case? Now the voltmeter indicates 1.556 volt. What does this mean? This means that UPN, which is equal to the voltage, is equal to VAG, the potential difference of the cathode, minus V for the anode, which is Zn. We will talk about what V means, which equals to 1.56. This means that UPN is equals to the electromotive force, if you still remember from the previous slide, is equals to VAG minus VZN. This equals to 1.56. So this is for the first. Let's just call it E1 is equals to 1.56, because this is the first cell diagram that we will start with. Now the second cell we will have is Cu as well. This is the anode, this is the cathode. Cu with Ag. Cu with Ag. Now here we have the Ag, here we have Ag plus. Again, I don't want you to forget that there is a spectator ion with the Ag plus. Here we have Cu2 plus. And we have Cu. This is the salt bridge. The electron flows from Cu to Ag. Okay, let me just say 2. Okay, from Cu to Ag. The current is the inverse from Ag to Cu. So the current from the cathode to the anode, the electron flows from the anode to the cathode. It's the inverse. And what happened? What did it indicates? The voltmeter indicates 0.46 volt in this cell. When we change the elements, the previous one we have Zn with Ag. Now we change it. It becomes copper with Ag. When we change the elements, the voltage is changed. Now we have 0.46. The previous one was 1.56. So the electromotive force is changing whenever we are changing the element. This means that the UPN of the cell is equals to V for the cathode minus V for the anode, V for Ag minus V for Z, no, this is Cu. Cu is equals to 0.46, right? Now, the electromotive force is equals to 0.46. We will call this E2 because this is our second cell. Okay, now these two, these two are not Daniell cell. Daniell cell is Zn with Cu. These are galvanic cell. We call them galvanic cell, but not Daniell cell. Now we have the cell diagram of the Daniels. This is Daniell cell. We have here, notice we talked about the Daniell cell in the previous lecture in the galvanic cells. This is Zn2 plus, again with the spectator ion Cu2 plus Cu, and here we have the salt bridge. We talked about the salt bridge as well. I'm not really interested now. We talked about the electron flow. It's from Zn to Cu. This is the electron flow, and the current flows from Cu to Zn. It's the inverse of the electron flow. And if you still remember that the Daniell cell UPN, the voltmeter indicates UPN is equals to 1.1 volt. And UPN is equals to VCU minus VZN is equals to 1.1 volt. This is UPN. Okay. Now we have three electromotive force. Now you know that UPN is equals to the electromotive force. Now we have E3 is equals to 1.1 volt. Now we have three values. We have three values of the electromotive force. Whenever we're changing the metal, the value of the electromotive force is changing. Whenever we're changing the cathode or the anode, the value of the electromotive force is changing. Now this is interesting, Why? Whenever we're changing the element, okay, or the metal, the potential, the electrochemical, the electromotive force is changing, and the potential difference is changing. Okay, which is logic, because UPN, as we mentioned, that the potential difference depends on the potential of the cathode minus the potential of the anode, right? That's why we call it the potential difference. So we have a subtraction here. So whenever we're changing the element, the metal, the potential difference, the potential is changing inside the cell. So this means that each half cell is characterized by a potential called reduction potential. So we call this reduction potential of the couple, Mn plus M. Each couple has a reduction potential. So the reduction potential of, let's say, in this case of Zn2 plus is different from that of Cu2 plus and Cu. And that's why we're getting different potential difference whenever we're changing the elements, the metals. Whenever we're changing the elements, we're getting a different reduction potential. Now, we will talk about how to calculate the reduction potential. But just you have to bear in mind that each element has its own reduction potential, or each couple, redox couple, has its own reduction potential. Now actually the reduction potential, now the potential difference and the electromotive force do not depend only on the reduction potential. It depends only also on other conditions, such as the concentration of Mn plus. So it depends on the concentration of Mn plus. When I say Mn plus, I mean this is the general form. Like we can say the Zn2 plus, the Cu2 plus, the Ag plus. The concentration of Mn plus, this is first. Now the second is the pressure. The third is the temperature. Okay? And that's why we have what's called the standard conditions of a half cell. We try to unite the conditions of a half cell. We call this the standard conditions of a half cell corresponds to the concentration of N plus ions should be 1 equals to 1 mole per liter. Okay, should be the concentration should be 1 mole per liter according to the standard conditions of a half cell, and the pressure should be 1 bar, and the temperature should be 25 degrees Celsius. So the electromotive force, to sum up what we talked about, the electromotive force or the potential difference of the cell depends on, first, the reduction potential of the half cell, second, on these three conditions: the concentration of Mn+, the pressure, and the temperature. To solve these three problems, we said that the standard conditions of the half cell should be 1 mole per liter, 1 bar for the pressure, and for the temperature it's 25 degrees Celsius. Okay? Now, I'm interested now in comparing redox couples to a reference couple. Okay? We have, in life, we have to make references. All the time we have to make references. The lion is big when comparing the lion to the rabbit, whereas the lion is small when comparing the lion to an elephant. So whenever we're comparing something, whenever we're calculating the size of the lion, we need to refer to something to calculate the size of the lion. We never say the lion is big by referring to the rabbit, or the lion is small by referring to the elephant. What I'm trying to say here, this means that we need a reference. Now, let's suppose our reference is Cu is VCU. I'm gonna take the copper as my reference, okay? VCU, and I'm gonna say that the reduction potential of VCU, the reduction potential of copper is equals to 0, right? I'm gonna say that. I can suppose that the reduction potential of copper is equals to 0. Now, in the case of Daniel's cell, the Daniel's cell, if you still remember that, in the Daniel's cell, E3 was 1.1 volt. Now we have E is equals to VCU minus VZN, the cathode minus the anode. Now here we have 1.1, right, is equals to VCU minus VZN. This is equals to 0. Now we have that the reduction potential of Zn is equals to minus 1.1 volt. Wait a second. Now, let's calculate the Zn and Ag. Now we have the Zn and Ag. The electromotive force is equals to 1.56. Now, comparing redox couples to a reference couple. Now, everything in life we need a reference to. The lion is big when it's compared to rabbits, but it's small when it's compared to elephant. So what's our reference here? Okay. Now, also in sciences we need a reference. We need a reference to value things. Okay, and that's why we invoked units. We said that this distance, we will call it meter. This is our reference, and the length of, let's say, of this table is 2 meters. Okay, so we have reference. Now in this case, let's suppose that VCU is our reference, and I'm gonna say that I'm gonna suppose that VCU is equals to 0. I'm gonna suppose I choose my reference to be VCU, okay, the reduction potential of copper, and I choose it to be equals to 0. Now I want to start with the Daniel cell. Okay, now Daniel's cell is equals to 1.1, so E3 is equals to VCU minus VZN is equals to 1.1. As we've mentioned before, the cathode minus the anode. Okay, now this is 0. Now VZN, I was able to calculate the reduction potential of VZN, which is equals to here minus 1.1. Now let's go to E2, Ag with Cu. Okay. Now in E2, it's VAG. The Ag was the cathode in this half cell minus VCU, which was the anode, is equal to 0.46 volt. So the reduction potential VAG is equals to 0.46 volt. Now, if my assumption is correct, I should calculate VAG minus VZN should be equals to E1, which is 1.56 volt. In E1 half cell, let's look in E1. The potential difference is E1, the potential difference of the cathode minus potential difference of the anode. Okay, in the cathode it was the Ag in our case minus V for the Zn. What is the reduction potential of Ag? It's 0.46 minus what's the reduction potential of Zn? We calculated it's minus 1.1. So E1 is equals to 0.46 plus 1.1. E1 is equals to 1.56. E1 we calculated through the potential difference. We calculated 1.56. The theory is applicable and it aligns with the observation, which was 1.56 in our case. We observed 1.56 in the voltmeter when we talked about this half cell, Ag and Zn. Okay, we observed 1.56. So supposing that VCU equals to 0 leads to correct conclusions. Again, supposing that VCU equals to 0 leads to correct conclusions. Now if we want to draw the electromotive force axis, we can say that here the couple Cu2 plus Cu, this represents the 0. Now VZN, the couple zinc is below, has a negative. You see the negative here. Okay, so it's below. It has a value of 1 minus 1, and here we have the couple Ag plus Ag is above, and it has the value 0.46. Okay, so if we talk about this, the axis, the electromotive force axis, this is the 0. This has a positive when we calculated by referring to the copper as a reference. When we calculated VAG was 0.46. It's a positive, so it's above it. Here we have minus when we calculated the VZ, and it has the negative sign, so it's below it. So why did I introduce you to the idea through we have the supposing that VCU equals to 0? Because I want to introduce you to the idea that we need a reference. And here comes the hydrogen half cell. Here it will be our universal reference. Actually, the hydrogen half cell is our reference, will be our reference in calculating the reduction potential, not the Cu half cell. Although we can make references by the Zn, but the universal reference here is the hydrogen half cell. Okay, so first I'm gonna talk about the compartment, how the description of the elements of the half cell. Okay, I'm gonna talk about the main compartments of the half cell in this slide. In the hydrogen half cell, as you know, the couple of the hydrogen is H plus H2. So we need to dip H2, somehow we need to dip H2 in H plus, as we were dipping Zn in Zn2 plus, and etc. So in other words, we need to dip the reducing agent in the oxidizing agent. Okay, The reducing agent is hydrogen, H2, and the oxidizing agent is H+. How we can dip a gas inside a solution? Well, through two phenomena. First is the adsorption. I'm gonna explain these two things before talking about the hydrogen half cell. We have a phenomenon called the adsorption. It's a physical phenomenon observed when molecules, gaseous or liquids only, are weakly bounded to the atoms of the solid surface. They form weak bonds to the solid surface of the of atoms of the solid surface. Okay. Now we choose that the platinum electrode. Why we choose the platinum electrode? We're gonna talk about it's a major part in the hydrogen half cell. The platinum electrode, we say it's platinum, but it's coated with platinum. It's not a platinum, it's coated. Platinum is expensive, so we coat the electrode with platinum. As I've mentioned, it's said to be platinum, but it's coated because it's covered with a layer of powdered platinum. Facilitates the adsorption of hydrogen gas. So first, platinum facilitates the absorption of hydrogen gas. Okay, and here we have the adsorption. What's the adsorption? Is when gaseous liquids, is a physical phenomenon where gaseous or liquids molecules weakly bound to the atoms of the solid surface. Now this is as you see in this photo, we have the hydrogen half cell. This is the salt bridge. We have here the hydrogen gas is being pumped at 1 atmosphere, and here we have the wire. This wire, we are dipping platinum inside the H+. Inside H+. The solution contains here H+. We are dipping platinum inside H+. Okay, so platinum is being dipped inside H+, and the hydrogen gas is being pumped through this tube going down to the platinum, here to the platinum. And the concentration of, as I've mentioned, as we've done this before, if you still remember, that the standard conditions, the Mn ions should be 1 mole per liter. So because of that, the concentration here of hydrogen should be 1 mole per liter, 1 molar. Okay. Now, why I have adsorption? What's the idea behind platinum and adsorption? Now, as I've mentioned, I need the hydrogen to be dipped inside the hydrogen gas to be dipped inside hydrogen ions. How I can do that? Through the adsorption of platinum electrode. Now, this is the platinum electrode. Okay. This is the hydrogen gas. Hydrogen gas will bond weakly to the solid surface of the platinum electrode. Hydrogen gas is a gaseous. Through adsorption, through this physical phenomenon, it will absorb and it will form weakly bonds with the surface of the platinum solid, as you see here, which makes the platinum is dipped inside the H+ ions, which makes the hydrogen gas dipped also inside the H+ ions, and that's why we use the platinum electrode and method. We use these two methods. The platinum electrode, we dip the platinum electrode, the hydrogen gas is going down to form weakly bonds on the platinum electrode. Why we choose platinum? Because it facilitates the adsorption of hydrogen gas. We dipped it inside. We dipped the platinum inside the H+ ions, so that the hydrogen gas will go down, weakly bonded to this platinum electrode. And when it's weakly bonded, because the whole electrode is dipped in H+, so the hydrogen gas will be dipped in H+. Okay, and that's why, if you still remember, when we have the beaker, let's talk about, like, let's say the zinc half cell. We have the zinc electrode. The zinc electrode was dipped in Zn2+. And this is the zinc electrode, right? The zinc metal. We're trying to make the same conditions here in the hydrogen half cell. We're trying to dip the H2 gas in H+, and that's how we did that. Okay? So now the SHE, or the standard hydrogen electrode, the role of the standard hydrogen electrode. We talked about the main compartments of the standard hydrogen electrode, how it functions. Now its role, mainly, as I've mentioned before when talking about copper couples, the metal redox couple of copper. Now we said that we need a reference, but the universal reference will be, in our case, is the standard hydrogen electrode, and will be for any metal, the only reference is the standard hydrogen electrode. When I just mentioned the copper as a reference, just to make sure that we need a reference when we have to calculate the reduction potential. So the standard hydrogen electrode is our reference. The reduction potential of the standard hydrogen electrode will be zero. And there are two conditions in the standard hydrogen electrode. The first condition is that the concentration of H plus should always be 1 mole per liter, and the hydrogen gas pressure should be always 1 bar. Okay, should be always 1 bar. So the standard hydrogen electrode is defined as the hydrogen half cell in which the concentration of H plus ions is 1 mole per liter and the hydrogen gas pressure is 1 bar. Now the cell notation of the standard hydrogen electrode, we start with PT, okay, H2, H plus. This is this is the cell notation of the standard hydrogen electrode. So if I want to construct the cell diagram, this cell diagram, let's say, containing standard hydrogen electrode, I'm going to just say PT, H2, H plus, salt to bridge. This is the first half cell, and I'm going to put here, let's say, Cu2 plus Cu. And the reaction undergoes in the standard hydrogen electrode is 2H plus 2 electrons. It's giving us H2. When I just write these two arrows, it means that we can start from H2 undergoing oxidation to have 2H plus 2 electrons, or okay, 2H plus undergoing reduction to become H2. Okay, these are the main reactions that occur in the standard hydrogen electrode. Actually, this is how the H2 undergoes oxidation. Okay, and this is how H plus ions undergo reduction. This is our reference, as I've mentioned, the standard hydrogen electrode. Now, we need to use the standard hydrogen electrode in order to calculate the reduction potential of metals. Let's suppose that we were able to form a standard galvanic cell with a hydrogen half cell and another metal. Okay, and another metal. And let's suppose that we need to calculate the UPN. The UPN is E, right? What's E? It's V for the cathode minus V for the anode. Okay, so this is V. This is E, the electromotive force. And then if I want just to say that I want to calculate, let's say, the metal, if the metal was the cathode and here the hydrogen half cell was the anode, this SHE, to be more precise, the SHE, the standard hydrogen electrode, is the anode, I can say that E is V for the cathode, or for the metal, minus 0, because we talked about that. The standard hydrogen electrode is 0 in the previous slide. Here, the reduction potential of the standard hydrogen electrode is 0. Now E, then this implies that E The electromotive force is V for the cathode, or in this case we have the metal that we want to calculate. How do we calculate E? E is equals to UPN. UPN is the number that the voltmeter indicates in the voltage. The potential difference, actually, the number that the voltmeter indicates, which means the potential difference. So it's easy. We need to construct the galvanic cell. Easy process. Construct the galvanic cell with a standard hydrogen electrode, and then we can first we need to know if the standard standard hydrogen electrode is anode or cathode before calculating the reduction potential of the metal, and then we substitute the standard hydrogen electrode with 0 and we calculate E. Okay, so here in this case we designate that E, it's become E node for the metal Mn plus M, the reduction potential. The standard reduction potential of the metal, when it's connected to the SHE, which is the standard hydrogen electrode, we designed it this way. And this could be negative or positive. It depends if the metal was cathode, okay, or if the metal was anode. This could be positive or negative or positive. So the relation that we talked about, okay, enables us to measure directly the standard reduction potential of any redox couple, of any metal, okay. The standard reduction potential, now it's designated by E node, and the E node can be positive or negative, okay, because we were able, now it's easy process, we were able to substitute the SHE with 0, and we calculate directly the E0 of Mn plus M, which we later can use. This is the reduction potential, actually. This is the reduction potential. We can calculate the reduction potential of any metal, and then we can use that if I have two metals without the SHE. For example, I calculated the E node for Zn, Zn2 plus, and Zn. Okay, and then I calculated through this method, okay, the reduction potential for Cu2 plus and Cu. I have now these two reduction potentials, right? Then I can conclude the UPN, or the electromotive force of the cell, because it's V for Cu because it's the cathode, minus V for Zn, it's the anode. Okay? Okay, so we're using this reduction potential just to calculate in other cells. We're using this reduction potential so that we can calculate the E in other cells. Okay, so the standard reduction potential of the Mn plus M couple is equal to the EMF of the cell, is equal to the EMF of the cell. The standard, I'm gonna repeat this sentence. The standard reduction potential of Mn plus M, okay, is equals to the EMF of the cell when Mn plus couple under standard condition is combined to standard hydrogen electrode. Because the standard hydrogen electrode equals to 0, then we are deleting this factor, then the electromotive force, okay, EMF, will be equal to the standard reduction potential of the metal. Okay, here's that. Concerning how we use EMF, I believe that it will become clearer if we do further applications. Now that's it for today. I hope that you enjoyed the video, and we will catch up later with probably with applications on galvanic cells. Thank you.